The following presentation has been modified from its original format to fit the constraints of present-day cognition. This is a short film about a real-time fractal voxel ray tracer. Any resemblance between voxels depicted herein and actual voxels, living or dead, is purely coincidental and not worth worrying about. Resolved. Tracing will displace rasterization. Discuss. And in fact, we are about to discuss it. This is really true. Tracing will displace rasterization. If you've read J.J. Gibson on the ecological approach to visual perception, if you're familiar with Gibson's corpus of work as the giant at the base of cognitive science bibliography chains, you'll recognize something of what's to come, or as a motivation behind some of my work. Basically, the best textures are geometric textures that come out of occluding geometry, and ray tracing doesn't have to suppress occluding geometry in order to get acceptable performance, whereas rasterization, the history of rasterization is a history of suppression of geometry in toy worlds. But today what I really want to look at is the landscape models in toy world renderers. And we'll be dipping into a couple other topics as well. So let's first think about Second Life. Second Life, we have a horribly ugly mesh landscape. In fact, it's one of the many worst things about Second Life is the landscape. The polygonal mesh objects are an addition to the landscape, but the landscape is just one mesh. Tunneling and mining is essentially impossible, and of course Second Life has a Baroque user interface with object crafting and scripting, and many in-world tools for writing code, testing code, building objects, and many of the things you can do in Second Life are completely worthy of emulation. The world that you see in Second Life was entirely constructed by the denizens thereof, using the in-world tools, and there's a lot to emulate and envy there. Second Life, of course, is written in C++ using OpenGL rasterization for the back end or front end. I can never remember which is which. I believe that a Second Life client may have been also coded in C#. Certainly, the server has been rewritten several times in C#. Now let's think about Minecraft. When I first saw Minecraft, I was amazed because I was amazed that a rasterizer could do that it wasn't doing ray tracing for visibility. In fact, the reason this is because I didn't understand how it worked at first. It works with chunk meshing, and so it's extracting potentially visible meshes from this landscape. So even though the block landscape in Minecraft is very, very complex and has unlimited numbers of blocks, and a huge number of blocks on screen at a particular time, if you think about the hidden blocks as being on screen, which of course they're not. But the reason this works is because only the potentially visible mesh is extracted from the chunk before the chunk is rendered. And there's not many potentially visible surfaces in there because it's mostly just a long stretch of air and then a long stretch of solid. And only air-solid interfaces are potentially visible. It's a procedurally generated block landscape with polygonal and textured flat polygon objects besides blocks in the world. And the flatness of the other objects, the the crude textures, is deliberate in the case of Minecraft because it seems to look better with a block landscape. There's no reason you couldn't have Second Life style mesh animated objects in a block landscape like Minecraft's. In Minecraft, there is no in-world creation of non-block objects. There is in-world creation and destruction of single blocks alone. You know, destroy a block, create a block. There's no in-world scripting. But the renderer is tunnel friendly. You can tunnel into the landscape. And while it's not a tracer, it's quite nice. It is of course written in Java and uses the lightweight Java game library, or possibly the JGL. Anyway, an OpenGL. Now let's talk about xnxl, which is the current incarnation of the Fractal Voxel ray tracer, real-time ray tracer that I've been working on for these many years. It has nested voxels. And what I mean by that is that there are larger ones and smaller ones, and the small ones can fit inside the large ones. So it could potentially be based on a 2x2x2 or 3x3x3 recursive division of space. Or in fact, since each of these schemes just leads to a particular voxel, and there's no reason you can't mix them, it actually could be based on any n by n by n recursive division of space, but those two are the most efficient. And there's no reason they can't be mixed. However, in the demo movies you'll see included here today, it'll all be 3x3x3 recursive subdivision of space. And the reason for choosing that, the 27 tree over the oct tree, is quite simple. If you have to choose just one, the 27 tree is better because you can directly represent a Sierpinski cube, and you can't do that in 2x2x2 because there's no inside to the block, to that unit. This uses Oberon, actually the active Oberon operating system, Blue Bottle, or formerly Blue Bottle, now called A2, sometimes AOS. The folks at ETHZ keep changing the name in a confusing way. This operating system is running in a window on Linux. It's a hosted version. And the reason for that is, well, it would work pretty well just on bare metal, except for the OpenGL front end that I've put on, or back end. I can never remember. All OpenGL is doing here is rendering flat quads interpolated between 4 adjacent rays at the very end, and scaling. So there's no 3D stuff being handled by OpenGL. What are the advantages over rasterization? Well, in this render there are mirrors, translucent color, Sierpinski cubes, huge cubes, small cubes, very, very small cubes. Space is a page. Functional representation objects functionally rasterized into recursively divided M space, what I call M space. But enough of the tedious exposition. Thank you for your extraordinary patience. Now, to the eagerly awaited code. And so let's just think about a single ray. Let's not worry about the sheaf of rays that make up the camera, or how those are rendered, how those are divided up and shaded in a parallelizable manner. Let's just think about a single ray being traced through space. And ray, as you can see, is a type, just a record type. And we're not concerned with the details, but you see that the ray has various points that it keeps track of. It has various colors that it keeps track of. It has booleans for things like Does it terminate? Has it reflected? Now, the world is made up of voxels. In fact, the world is a voxel containing other voxels. The world is just a voxel. A voxel is an object, and here's the base type for voxel. I've taken out most of the methods. Voxel is an object. It has a few fields in it. Most important one for our purposes here being code. We'll see that later. And every voxel has a procedure shade, which takes array and changes it, possibly, and then returns. Now, the whole tracer is based on this. So, let's look at a colored cube. So let's subclass voxel in the most brain-dead, easy way we can think of, and make a colored voxel. So what does this say here? Well, it's just a voxel. It inherits from voxel. It has 3 reals fields, which are the red, the green, and the blue value that it has, and we can set those values with this procedure, and it re-implements shade. And when it gets an array that has hit it, it doesn't pay any attention to the coordinates at which it has been hit. All it does is it colors the array according to its color, and it terminates the array and it hands it back. More complicatedly, let's look at a mirror cube. So a mirror cube has some colors. I suppose it could be a colored mirror, but all it does is it checks which face it has been hit on when it's shading the ray, and it adds a little bit of darkness. And the reason for that is that if you have mirrors that are perfectly reflective in the world, they can trap rays. If you have 2 of them, those mirrors, they can trap a ray between them and it will never terminate. So obviously the way to avoid the renderer locking up because the ray never terminates, which happened when I implemented mirrors first, it locked up and I laughed because I realized why it had locked up. It had locked up because the mirrors were trapping the rays forever. So it adds a little bit of darkness by decrementing the 3 different colored alphas, and it mirrors the ray. And mirror is just a procedure which does a little math on the ray. Now, M3 space, which is the 27 cube, 27 tree, is defined in its own module, but it's just another kind of voxel. And in fact, this module is written so that all I have to do is change a few numbers, in particular this one, M, and I can make an 8 tree. I could change that to 2 and make an octree module. I could change it to 4 and make a 64 tree module, and so forth. So you can think of it as my equivalent to C macros, right? Which is just changing by hand a few things about a module and recompiling it. But cell is the 27 tree voxel, and it just has an array 3 by 3 by 3 of voxel inside it. And the shader for this is very complicated, however, as you'll see. In fact, if I wanted to get it all on camera at once, I would have to make it too small to read. But basically the shader just steps through space, intersecting the ray with the subcubes, and recursing the shader down into them. That's basically what it does. So that's all the prepared show notes I have. I figured by this point I'd be rolling well enough that I could just start riffing, and in fact I believe that to be the case. So we have a world, we have this system set up. Now, how do I set up the world and define what it looks like? I do it at first procedurally in this module here. So I'm going to leave this here and come back and record more later.